Right now, somewhere beneath the warm turquoise waters off South Florida's coast, the ocean floor is caving in. Not from a storm, not from a hurricane. The ground itself is failing, silently, invisibly, and faster than anyone predicted. Why are massive voids appearing overnight on the seafloor near Miami? Why is the limestone beneath one of America's most populated coastlines dissolving at an accelerating rate? And what happens when the foundation holding up a metropolitan area of more than 6 million people simply stops being there? No one standing on the white sand beaches of Deerfield Beach would have suspected what lay just offshore. The water was calm, the tide was ordinary, but beneath the surface, the earth had opened its mouth. A routine Coast Guard patrol detects something that doesn't belong, an anomaly on the depth sounder. Where the seafloor should read 12 meters, the instrument shows 30, then 40. Based on what we know about Florida's offshore karst features, a scenario like this is not only plausible, it may be inevitable. Divers are dispatched. What they find is not a shipwreck, not a trench, not a geological formation anyone has cataloged. It is a gaping void in the ocean floor, roughly 40 meters across and still widening. USGS seismic reflection studies have confirmed that sinkholes do breach the seafloor off Florida's coast, and dissolution collapse structures originate deep within the carbonate section. But this was only the first warning. Within 72 hours, additional sonar sweeps near Pompano Beach reveal a second collapse, then a third near Boca Raton. In this scenario, they are not random sinkholes, they are aligned along the same subterranean corridor, like wounds opening along a single fracture. Beach sand begins migrating toward the offshore voids. Shoreline contours shift visibly in satellite imagery, changing shape over the span of days rather than decades. Emergency management teams scramble, but there is no protocol for this, because this has never happened before at this scale. And the seafloor was still moving. Authorities issue closure orders across 47 miles of coastline from northern Miami-Dade through Broward and into Palm Beach County. Resort pools drain toward invisible cracks. Tourists are evacuated from beachfront hotels in the middle of the night, carrying suitcases through lobbies that smell faintly of sulfur. Sonar imaging teams work around the clock, mapping the seafloor in overlapping grids. By the end of the first week, they have identified 23 distinct underwater collapse points scattered across the continental shelf. The collapses range in diameter from 15 to 60 meters. What came next shocked even the scientists.
The individual sinkholes are not isolated. Deep penetration sonar reveals lateral connections between the voids, narrow channels of dissolved rock linking collapse to collapse like the tunnels of an ant colony. This is not a cluster of random failures. This is a network. University of Miami geologists run the first preliminary models. The results suggest what could be a continuous zone of compromised limestone running parallel to the coastline, a subsurface corridor where the rock has been chemically weakened over millennia and may now be giving way in cascading sequence. If confirmed, the implications would redefine how we understand coastal karst failure. To understand why this is happening, you have to understand what Florida is built on. The answer is almost nothing. The entire state sits atop a platform of carbonate rock, principally limestone and dolomite, deposited over tens of millions of years on an ancient seafloor. According to the USGS, about 20% of the land surface in the United States is classified as karst terrain. Florida sits squarely within some of the most extensive and active karst landscape on the continent. Limestone is strong under compression, but it has a fatal weakness. It dissolves. Slightly acidic rainwater, carrying dissolved carbon dioxide from the atmosphere, percolates through soil and seeps into the rock below. Over centuries, it opens pores. Over millennia, it carves tunnels. Over geological time, it hollows out vast underground chambers. The Florida Department of Environmental Protection describes this as the process that creates caves, springs, sinkholes, and underground drainage systems throughout the state. But the process was supposed to be slow. Now, something is accelerating it. Saltwater, denser, more chemically aggressive than fresh groundwater, is pushing inland through the Biscayne Aquifer at rates that alarm hydrologists. USGS mapping shows the saltwater front in southeastern Miami-Dade County advanced inland at approximately 100 meters per year between 2014 and 2018. Miami-Dade County's own resilience reports confirm that this intrusion threatens the region's primary drinking water supply. When saltwater enters porous limestone, it does not just contaminate the water, it changes the chemistry of dissolution. The mixing zone between fresh and saltwater creates a uniquely corrosive environment, more aggressive than either fluid alone. Geologists call it the mixing zone dissolution effect. It eats rock from the inside. And no one was watching the underside of the coast. Emergency sonar mapping and university modeling begin to reveal what could lie beneath the developed coastline itself. Cavern systems, some with chambers that could exceed 30 meters in width, are the kind of features geologists have long suspected exist beneath residential neighborhoods. Given that the Biscayne Aquifer is characterized by highly permeable karstic limestone with interconnected vug porosity, such voids would not be surprising, yet most have never been mapped. The Floridan Aquifer system, one of the most productive in the world, underlies all of Florida and extends into parts of Georgia, Alabama, and South Carolina, roughly 100,000 square miles of interconnected carbonate rock, according to USGS Professional Paper 1403. Its structure is riddled with dissolution features at every scale. The question is no longer whether voids exist beneath Florida's cities. The question is how many and how close to the surface. But the ground had one more secret. Researchers identify multiple compounding stressors converging on the region simultaneously. Sea levels along the South Florida coast have risen approximately 15 centimeters over the past 3 decades, consistent with NOAA tide gauge records. This rise pushes the saltwater interface deeper into the aquifer, accelerating the chemical weathering of limestone from below.
Meanwhile, groundwater pumping to supply Miami-Dade County's nearly 3 million residents withdraws roughly 420 million gallons of fresh water per day from the Biscayne Aquifer. Every gallon removed lowers the freshwater head, the pressure that holds the salt wedge at bay. The result is a geological pincer movement. Rising seas push in from one side while falling water tables retreat from the other. In a scenario of accelerating subsurface collapse, monitoring stations deployed along the coast would likely begin detecting low-frequency acoustic emissions, faint pulses in the 1 to 10 Hz range, consistent with the sound of rock fracturing deep underground. Such signals, if they appeared, would be intermittent and difficult to localize, but based on what we know about progressive cavern failure, they would grow more frequent. What no one expected was what washed ashore next. Along a 30-kilometer stretch of beach, thick ribbons of black, tar-like material begin appearing in the surf zone. Emergency responders initially suspect an oil spill. Coast Guard overflights find no vessels in distress. No pipelines in the area are compromised. Laboratory analysis reveals something far stranger. The material is not petroleum. Based on its composition, it appears to be ancient organic matter, decomposed plant and animal material that could have been sealed within limestone strata for tens of thousands of years, now released as the rock containing it collapses and dissolves. If carbon dating confirmed samples at over 40,000 years old, it would mean something locked in deep geological time is now breaching the surface. In such a scenario, methane readings would likely spike along beach monitoring stations. Marine biologists could report unusual fish kills in nearshore waters. Seabirds would avoid previously active feeding grounds. Something sealed deep in the rock for millennia would be entering the ocean in quantities large enough to detect from shore. And then the damage reached the surface. Maria Delgado has lived in her single-story concrete block home in Hollandale Beach for 23 years. She raised 2 children there. She knows every sound the house makes, the settling of roof tiles in the afternoon heat, the whisper of the air conditioner cycling on. But in the 3rd week of the crisis, she hears something new, a low groan, almost subsonic, that seems to come from beneath the foundation. By morning, a crack has appeared in the kitchen floor, thin as a pencil line, running diagonally from the back door to the sink. Within 3 days, it widens to 4 centimeters. The front porch tilts. A window frame warps and will no longer close. I put my hand on the wall and I could feel it moving, not shaking, moving, like the house was breathing. She is one of hundreds. Across the affected corridor, buildings develop cracks in foundations and load-bearing walls. Several commercial structures in Fort Lauderdale are evacuated after engineers detect differential settlement, one side of a building sinking faster than the other. A section of Highway A1A1 near Pompano Beach subsides by 12 centimeters, forcing lane closures. High-rise condominiums along the coast trigger emergency structural reviews. The memory of the Champlain Tower's south collapse in Surfside, which killed 98 people in 2021, hangs over every inspection. Foundation engineers probe for voids beneath pilings. Some find them, and the signs were already spreading. Florida begins recording something it almost never experiences: earthquakes. Small ones, barely perceptible, magnitude 1.5 to 2.3 on the Richter scale. Florida sits far from any tectonic plate boundary. Under normal circumstances, it should not shake. But cascading underground collapse would change the equation. Seismologists propose non-tectonic explanations that could account for such tremors. The collapses themselves would generate seismic energy, small but detectable. Rapid redistribution of underground water pressure as caverns flood or drain can produce similar signals. Progressive cavern failure, one chamber collapsing and transferring stress to the next, would create a chain reaction that propagates through the rock like a slow-motion earthquake. Temporary seismometer networks are deployed across the affected region. The instruments detect not individual events, but a continuous low-level tremor, a geological murmur that suggests the subsurface is in constant, restless motion. No one had heard Florida make this sound before. Attention expands beyond the state border. Officials in Georgia and South Carolina initiate precautionary geological surveys of their own coastlines. The reason is simple and alarming. They share the same aquifer. The Floridan aquifer system extends beneath all 3 states, a continuous body of permeable carbonate rock spanning 100,000 square miles, according to USGS mapping. Researchers at the University of South Florida introduced what they call the domino theory of karst failure. The underlying logic is straightforward. Pressure changes in one part of a connected aquifer system can propagate through groundwater pathways and, in principle, destabilize rock hundreds of kilometers away. If saltwater intrusion and dissolution are accelerating in South Florida, the same chemical processes could already be at work beneath Savannah, Charleston, and Jacksonville, cities built on the same dissolving foundation. The theory remains unproven at regional scale, but given the connectivity of the Floridan aquifer system, no researcher has been willing to dismiss it entirely. The economic implications arrive before the geological ones are fully understood. Tourism, the industry that generated over $130 billion in economic impact for Florida in 2024 alone, takes an immediate hit along the affected coast. Hotel cancellation rates surge, cruise lines reroute departures, beach-dependent businesses close indefinitely. Coastal real estate enters uncharted territory. Properties within the affected zone see listing prices frozen or withdrawn entirely. Research from Florida International University has shown that proximity to a known sinkhole location reduces residential property values by 2 to 9%. But this is not a single sinkhole. This is a systemic geological event affecting hundreds of square kilometers. Insurance companies begin issuing non-renewal notices for sinkhole endorsements in affected zip codes. Florida law requires insurers to offer sinkhole coverage but does not cap the premiums. Some carriers quote rates that effectively make coverage unaffordable, $5,000 or more per year on top of already elevated homeowners premiums that average $11,000 annually statewide. Mortgage lenders in affected areas tighten lending criteria. The financial architecture that supports coastal living begins to wobble. But the crisis had not peaked. 1 week passes. Surface conditions appear calmer. Beach erosion slows. The black tar stops washing ashore. News crews pack up their satellite trucks. Officials cautiously suggest the worst may be over. But the monitoring data tells a different story. Underwater sonar shows that the seafloor voids have not stabilized. They have merely slowed their expansion. New collapses continue to appear at a reduced but steady rate. The low-frequency acoustic emissions from underground actually intensify during the quiet period, suggesting that stress is redistributing through the rock rather than dissipating. Displaced residents remain in shelters. Building inspections backlog into weeks-long waits. The crisis has not ended. It has simply become invisible again, retreating beneath the surface where it has always lived. This was never a fast disaster. It was a slow one, finally arriving.
The long-term implications force a confrontation with uncomfortable truths. Critical infrastructure across South Florida, water treatment plants, electrical substations, hospitals, transportation corridors, sits on the same porous limestone that is failing offshore. Turkey Point Nuclear Power Plant operates just 25 miles south of Miami, its cooling canals carved directly into the porous limestone of the Biscayne Aquifer. Further north, St. Lucie's reactors sit on the Atlantic coast. Major ports that handle billions of dollars in cargo annually rely on foundations driven into rock whose long-term integrity is now open to question. Climate projections from NOAA and the Southeast Florida Regional Climate Change Compact estimate sea level rise of 0.5 to 0.7 meters by mid-century and up to 1.5 meters by 2100. Each centimeter of rise pushes the saltwater front further into the aquifer. Each advance of the salt wedge accelerates the dissolution of the rock that holds everything up. The process feeds itself. Some geologists caution that similar conditions could already exist beneath other coastal regions built on carbonate rock, the Yucatan Peninsula, parts of the Caribbean, sections of the Mediterranean coast. If that assessment holds, Florida may not be an anomaly. It may be a preview. And the question no one can yet answer is the one that matters most. We built a civilization on rock that dissolves in water. We pumped the water out from below and let the ocean push in from the side. We loaded the surface with concrete and steel and more than 6 million lives. The limestone held. For decades it held. But limestone does not warn you when it is about to stop holding. It does not crack loudly or shift visibly or send alarms to your phone. It simply becomes less, quietly, invisibly, one dissolved grain at a time, until the day there is not enough left to carry what we placed on top of it. That day may be approaching. It may already be here. And if the ground beneath South Florida is already too far gone to recover, if the dissolution has crossed a threshold that no amount of engineering can reverse, then the question is no longer whether Miami's foundation will fail. The question is whether we will know before it does.